Okay, now we're going to talk about the effect of a phenomenon known as shear lag, which is how forces lag within a cross section, right? So if I've got this connection subjected to a tensile load, the forces are going to transfer from the plate to the bolt. Kind of like flowing, right? Right, if you're pulling, you're gonna feel it in the middle first, and eventually get to the bolts, right? It's called the flow of forces. Now imagine if we had a much wider plate. And my forces were flowing from the bolts. Right. Well, I just said earlier, where am I going to fail? Right here. Oops. Right at the right? That's my rupture plane. But right, this is my rupture plane. Oops. Make that a little bit nicer. But due to the flowing of forces between transferring the force from the plate to the bolts, right, along this line and along this line, by the time I get to my rupture plate, not all of the member is actually participating. The force hasn't been transferred. So there's a portion that's carrying actually no tension. And if we assume that this happens at a 30-degree angle, this length right here, oops. This is called LW. This is called the Whitmore section, the section that's actually actively resisting. And this is the effective length, right? Of the rupture plane. So if I have a really wide connection, especially compared to its length, not all of the members actively resisting the tensile load at where I would have my rupture happen at that lead bolt line. And so we have to account for that. And that is known as shear lag. I have an in-class activity that if I were in class with everyone, I would do. I might have some family members participate instead to help visualize shear lag. So I'm sorry that we're not going to be able to do it in person. It does involve holding hands, which is probably not good during a pandemic anyway. But yeah. So shear lag is a phenomenon that accounts for the distance required for stresses to distribute from connectors to the full cross section. Right? It takes a while to distribute that entire load over that cross section. It mostly occurs when only a portion of the cross section is connected, and we'll show what that means in the next slide. Or if you don't have a really long section, especially compared to its width. So we have a net area that we calculate in which we, right, subtract our bolt holes. And then we need to account for this shear lag and calculate our effective net area. Right? They are not equal due to shear lag. Well, they may not be equal. There are instances when they can be equal, but they may not be equal due to shear lag. So first you have to calculate a net area, and then you have to multiply it by some factor to get your effective net area. So let's look at an angle that's only connected on one of its legs. This is what it means when not the entire cross section is connected. If I apply a tensile load here, right, and I'm going to draw my rupture plane coming out at that 30-degree angle from that last bolt hole. That's not my rupture plane, that's my stresses. So that means that only, right, if this is, if I draw it from the other side too, the only the things that I'm coloring in are resisting that force. due to shear lag, I'm drawing that 30° from that last bolt hole. So then if I look at that lead bolt line, right, it's only one bolt. And I draw it up here. This is my rupture plane. Right, not the entire cross section. This little portion up here. Not resisting PM. So I don't get to use my entire cross-sectional area, even subtracting out the bolt holes. I don't get to use all of that when I'm calculating my effective area in my rupture limit state. And that's what this little drawing is saying. Only the sections in black, right? I don't like that. Only these sections. This is my cross section at the bolt hole where I'm going to have rupture, at the bolt line where I'm going to have rupture. Is effective. This little section right here is not doing anything. It's just hanging out, being a lazy bum. And the reason it's not effective is due to shear lag. So, just to reiterate, shear lag is less influential if the connection is long, right? If I had a bolt hole like way out here and I drew, way out here maybe, and I drew that 30°, by the time I got to that first bolt line, it would all be effective. But because I have a shorter distance from my last bolt hole to my lead bolt hole, I have shear lag. So it's less influential if your connection is long, or if your outstanding leg has minimal area of eccentricity, as in if this was shorter, right? If there wasn't that long of a leg on the not connected part of that angle, then it wouldn't be as big of a deal. I mean, you would still have less cross-sectional area because you'd have a smaller cross-section to begin with, but shear lag wouldn't affect your effective area as much. Wouldn't affect your effective area. Yeah. My affect and my effect, right? So that is all about shear lag, and I'm gonna see if I can come up with something to help illustrate it a little bit better. So now we've talked about yielding and rupture and the effect of shear lag. And next up is going to be talking about block shear.